Hi, everyone. My name is Harley Jackson. I'm a student in the MS ECE program at Purdue University by night and weekend. And during the day, I'm a software engineer for LinkedIn. And today, I want to talk to you about my project for epidemic processes over networks. And it's called Identifying Epidemic Parameters of COVID-19 based on US case data. Yeah, so as I'm sure everyone knows, the COVID-19 virus has been infecting individuals around the world for over a year. So it's a global pandemic with global impact. And in general, mathematical models predict how the disease will spread under different conditions and how to stabilize and possibly eradicate disease spread. And one paper pointed out that COVID-19 is best modeled under SIR since there's no strong evidence of becoming reinfected with the virus after recovery. All right, so with that background, the goals of my project include identifying the parameters of the SIRD model for COVID-19 using public test data made publicly available by the CDC. So we added I added a separate compartment for deceased. And the reason is that essentially like deaths are, important and probably like the most important thing to try to prevent. So it was important. I considered it important enough to take a look at it. And while moving into the recovered compartment is probably considered a good thing, moving into the deceased compartment would not be. So once the parameters for the SIRD model are calculated, a Jacobian local analysis is carried out on the the infected and deceased compartments to see what conditions are necessary for them to locally converge to zero, because essentially these are the two compartments that we want to converge to zero. Other goals were use the Erdos-Renyi method to generate random network connections and compare a network version of the model to the group model. And what we'll see later, or what I'll explain later is I wasn't actually able to do this due to some challenges. So I'll explain that later. And then the idea would have been, if we had the network model, to change the probabilities of random interactions based on a given month due to varying policies that would have, decreased the likelihood of being exposed. Okay, so I chose to go with Python for my data cleaning and analysis. This is just a personal choice. I'm a bit more familiar with the Python suite than MATLAB. MATLAB, my experience is basically limited to this class, this series of classes. So yeah, matplotlib for graphing using Python 3.8, NumPy for matrix operations. A Jupyter Notebook is where I carried out the actual analysis. This helped me to experiment and keep track of the different outcomes that I got. And pandas is how I maintain my data flow. So some characteristics of the data. So a big factor is that there's over 20 million rows. Each of these represents a case. So 20,565,345. Each of these rows has 12 fields, and the descriptions, they're coming from a form that's publicly available. And here are the fields. They are CDC report date, positive specimen date, onset date. And then we have a field called the CDC case earliest date, which is essentially an argument of these three. So this was the field that I used to transition a case from susceptible to infected. And the other ones include current status. There some demographics such as sex, age group, race, ethnicity, and some binary variables that can help with identifying severity, such as hospital yes or no, ICU yes or no, death yes or no, and medical condition yes or no. So out of these fields, these other fields, the only one I used was death yes or no. The reason is, the reason I chose to go that route was it helps to describe, it helps to develop the deceased compartment. And the other thing was I felt like the hospital yes, no, and ICU yes, no were not really consistent enough to use for severity. But yes, that was just a choice that I made. Okay, so the procedure I followed. I cleaned the data by ensuring that the field CDC case earliest date field is valid and doesn't have any missing values. It actually turned out to be that none of them were missing, which was great. So I didn't have to drop any rows. And some of the rows had in death yes or no, either missing or NA, and I just went ahead and converted those to no instead of dropping them. So unless it says yes, we assume no. And yeah, so again, I'll explain this later, but I had to take a different approach than my original intent due to computational complexity, or it's actually more about memory, I'm assuming. So yeah, I generated 4 new columns to assist in aggregating the fields. Basically, one is the infection time. It's the date that the infection is in onset, and then the date when the infection ends. So this would be regardless of which compartment you transition to after that. You know, it just helped with the aggregation. And then there was recovered time if they recovered. If not, basically it was assigned a -1. Or deceased time. Again, the date that they were deceased, assumed to be deceased, or a -1. So essentially one case cannot be in both recovered and deceased. It's one or the other. So the way that I calculated infection end time was essentially if they had recovered, I added 11. This is based on the observed average duration of a mild case, which is 10.63 days, plus or minus. So we went ahead and just used 11. So this comes from a study. Infection end time. It's equal to the date of infection plus 19 days if they died. So basically, this came from the same study where severe cases were found to be 18.7 days plus or minus 2.5. And yeah, so we went ahead and assumed that if they died, it was severe. So yeah, basically, like I said before, we set it to -1 if they did not recover or if they did not die. And then using these using these 4 columns, I calculated the number of people in each state, SIRD, at day T, where T is in the range 0 to 409, because the data set had 410 consecutive unique days starting at January 1st, 2020. So 0 is that date. After the data frame of SIRD values was generated, all values were divided by the US population at T equals 0, which was 329,168,006. And this was also taken from census.gov's population clock. The other thing I'd like to point out is that the susceptible group would be all of the cases until they got infected. And, you know, so what I had to do is add, basically what I did is I took this number and I subtracted the number of cases in the study. So 20 million something. And then that way S started at 100% or 329,168,000. Okay. So that was before dividing to normalize it. All right, so a little state diagram of the SIRD model. So we're calling the parameter from S to I beta, and then we have gamma into recovered or delta into deceased. Okay, so this is how the proportion of the population in each bucket or state changed over time. So we can see that recovered is starting to go up here, and then we see that susceptible is going down. This is because we're assuming that once you've recovered, you're not going to be susceptible again. And since the and we can see that it ranges from 0 to 1, so it has been normalized. And over here, I just broke them out into some graphs because of this way we could get a closer look at what each one's doing. So as you can see, towards the end, it looks like over 6% have been infected based on the population size we're using. And we can see in the IRD, we can see how the infected amount has some kind of peaks, but it does look like it's declining. So yeah, it seems like whatever interventions were being taken around this range of time appear to be happening, or sorry, appear to be effective, right? So, okay. Okay, so the way that I derived the basically set up the equations to try to identify the parameters is, starting it out by modeling the behavior of each state in discrete time, right? So we know that beta S time I is how it's going to change that's how the amount of S is going to change for one time step. And same with I, R, and D. And then essentially putting these into matrix form, and then going ahead and manipulating the matrix so that our outputs are beta, gamma, and delta. So I went ahead and set H to 1. And I observed that because beta, gamma, and delta can totally be determined with S, I, and R, we could go ahead and omit state D. This gives us a 3x3 matrix to invert and still determine the parameters. Okay, so essentially this is the derivation and then coding this up in NumPy in the Pandas notebook. Okay, so the parameters over time. So this is basically like I computed what the parameters would be for each time step, t and then t plus 1 from 0 all the way forward to 409. And so you can see here beta starting up very high and then declining, and then you see some some times where it kind of goes up, some peaks, and you see gamma and you see delta. So again, I did some breakout graphs so that we could see more details of how each one was behaving. Like for example, delta, which is the way that people are transitioning from infected to deceased, is it looks flat on this graph, but when you zoom in, you can see that there are definitely big changes. And it looks like there was a peak here. So there's a period where the movement from infected to deceased was higher than later on. So it does look like this got controlled, which is good. We want this to be 0 essentially. And yeah, and then you see how gamma is behaving. Little spike here, one in the beginning. But yeah, this one is, I mean, we'd rather people not get infected at all, but if they get infected, we would rather them recover than die, for sure. Okay, and then the Jacobian analysis on buckets I and D. So essentially the behavior can be modeled in this fashion. So the delta, or the change in I would be equal to I times this value. And the change in D is also dependent on I. So we just keep D here to make it a 2x2 matrix. And if we set S star, then this is how the graph changes, or the matrix changes. And then if we set S star to 0, we essentially get this matrix here. And then we can see that it should converge locally to 0 when negative gamma minus delta is less than 0. So this, as you can see, this doesn't necessarily, yeah, actually, like, yeah, I'm interested in finding out if I did this correctly or not, because this implies that even if the death rate was going up, it would actually be closer to stabilizing, which wouldn't be desirable necessarily, or of course wouldn't be most desirable. Okay, so the challenges and limitations I wanted to point out. So the original plan was to replace each row with 410 states. So each of the 20 million something rows with 410 states, so that you know, the networking part could be carried out as well. So one thing I found out though is that when I was replacing each row with 410 states, basically what state that row would be in per day, the computation time took, it was like, not essentially, well, yeah, it's essentially unlimited for my purposes. Like 24 hours, I only had about 155,000 done after I interrupted the process. So there's a really good chance that it was occupying all the memory. So it didn't have any space to basically continue. That's my guess. But anyway, this is the reason why I had to refactor my approach. And yeah, in the data, there's no recovery date. So the recovery time was inferred as the average taken from the literature, which I explained in the procedure. And yeah, in the data, there's no network information. This was the reason for the idea of doing a Erdos-Renyi analysis, where we randomly assign networks just to see how the behavior could be. But yeah, wasn't able to carry this part out. And the other like limitation is assuming the US population is the same over the course of 410 days, which it's not. Realistically, every single day was different. I chose to just divide all the values by the same population, the population at t equals 0. But yeah, that's another limitation of the study. So thank you for listening to my presentation. And all of this data will be made available on GitHub, including the Jupyter notebook I used. And yeah, the paper will have citations, and that'll be linked in the README. Thank you. Have a good one.